For the first time, the mystery of the black hole has been unveiled. In February 2025, astronomers using NASA's James Webb Space Telescope obtained the most detailed images of the mysterious black hole hidden in the core of our galaxy. The supermassive black hole at the center of the Milky Way put on a grand light show, akin to a disco. Researchers recorded that the rotating gas and dust disk surrounding the central supermassive black hole known as Sagittarius continuously emits flares of varying intensity. The activity varies over a wide range of time frames, from instantaneous pulses to long cycles. Some flares appear as faint flickers lasting only a few seconds, while others are powerful outbursts that occur daily. In addition, there are less intense changes observed that stretch over months. These findings promise to shed light on the deep nature of black holes, the mechanisms of their feeding from surrounding matter, as well as the dynamics and development of our galaxy. We recorded a continuous change in brightness, said Farhad Yousafzadeh from Northwestern University in Illinois, who led the research. From time to time, a powerful flare would suddenly appear. Then everything would calm down. We did not find a clear pattern in such activity. It seemed chaotic. Every time we observed this black hole, its behavior was new and exciting. To conduct the analysis, Yousafzadeh and his colleagues used the Webb NIRCam near-infrared camera. For 48 hours, scientists tracked changes in the behavior of Sagittarius A** with intervals of 8 to 10 hours. Over the course of an entire year. This allowed them to track how the black hole changes over time. Although the researchers expected to see flares, the activity of Sagittarius A** was significantly higher than anticipated. Observations showed that continuous flares of varying scale and duration occur constantly. The gas and dust ring surrounding the black hole produces 5 to 6 significant flares, interspersed with numerous smaller bursts. Daily. Black holes are celestial bodies with such a powerful gravitational field that nothing, whether matter or radiation, can escape its pull. According to classical general relativity, all the matter that formed the black hole eventually ends up inside it and reaches colossal, or even infinitely large density. This concept is known as the singularity problem. Black holes affect the geometry of spacetime. The bending of spacetime causes a gravitational lensing effect, where light rays passing by the black hole are distorted and deflected. Since a black hole deforms space and time, the existence of a wormhole is possible, which is a tunnel connecting different regions of spacetime. Imagine a sheet of paper with 2 points drawn on it, point A and point B. These points are located on opposite edges of the sheet, similar to objects situated at the farthest reaches of the universe. To connect points A and B, you need to draw a straight line across the entire sheet from one point to the other. But if you fold the sheet, the paper, like spacetime under the influence of a black hole, begins to bend. As the sheet is folded, points A and B come closer together without moving themselves. This connection between the points represents the tunnel, or wormhole. Black holes can come in a wide variety of sizes, from microscopic scale to sizes beyond imagination. The smallest of them are comparable in size to a single atom, yet they have the mass of an entire mountain peak. For those who don't know, mass is a measure of the amount of matter contained in an object. Stellar black holes can reach masses more than 20 times that of the Sun. However, the most impressive are the supermassive black holes, whose mass exceeds that of our Sun by millions of times. Such giants reside in the hearts of the largest galaxies. Our galaxy, the Milky Way, also has a supermassive black hole. Known as Sagittarius A**, its mass is equivalent to 4 million solar masses. This monster can contain millions of Earth-sized spheres, and it is in this. NASA scientists have discovered flashes of light, which I have already mentioned. All objects in the universe create a distortion of space and time around them. The more compact the body, the stronger this effect manifests. Compactness is determined not only by the size but also by the mass of the object. Even a small body with a large amount of matter can have significant compactness. Black holes represent the extreme degree of this phenomenon. Regardless of the original material, whether it's a gas cloud or a neutron star, with sufficient compression, any body turns into a black hole. Inside such objects, completely different physical laws operate, and information that enters there can no longer return. It is this mystery that makes black holes so intriguing. There are two key directions in the study of black holes. The first is physical, where the main focus is on the properties of these objects, including internal processes. The second direction is astrophysics, which identifies four main types of black holes. The most well-known are supermassive black holes, present at the center of almost all large galaxies. The masses of such objects range from several thousand to tens of billions of solar masses. Another important type is stellar mass black holes, which form during the evolution of stars. After the completion of thermonuclear reactions in the core of a star, a heavy iron core is formed, which subsequently undergoes gravitational collapse or, in other words, a systemic process of destruction. Although not all of the star's material ends up in the newly formed black hole, its mass can still exceed the mass of the Sun by dozens of times. Intermediate mass black holes also stand out, occupying a niche between stellar and supermassive objects. The origin of such holes remains unclear, although there is a hypothesis that they could have formed as a result of the merger of massive stars. In dense clusters, there are finally primordial black holes that appeared shortly after the Big Bang. The peculiarity of these objects lies in their early origin and the wide range of possible masses, from enormous to microscopic. Despite numerous searches, the detection of primordial black holes remains a task for the future. The general theory of relativity states that matter, when forming a black hole, continues to compress to the state of a point, after which it ceases to exist, leaving behind a singularity. It turns out that inside a black hole, the usual forms of matter, protons, neutrons, quarks, and other elementary particles are absent. All of this disappears, transforming into pure energy, which causes space-time to curve. The closer to the center, the stronger this curvature, reaching its maximum at the singularity itself, where the curvature of space-time becomes infinite. Simply put, matter can be imagined as a needle that pierces the fabric of space and time. After that, the needle is no longer needed. It has fulfilled its function, transforming into a force that maintains the open puncture. In other words, the needle is gone, but the hole it left remains. However, it should be noted that this was about non-rotating black holes. Most stars, from which black holes emerge, rotate, passing this motion on to their descendants. In that case, the singularity takes the form not of a point, but of a ring with zero thickness. What lies inside this very singularity? There are many different hypotheses. I will tell you about the one that most scientists around the world adhere to. It is assumed that the structure of a black hole includes two key components. The first of them is the event horizon, which represents a boundary in spacetime through which matter and light can only move inward. No information, not even light, can escape beyond this boundary and become accessible to the outside world. For observers located far from the black hole, clocks near it will appear to be running slower than those located at a greater distance. This phenomenon is known as gravitational time dilation. Because of it, it seems as if an object falling into a black hole slows down as it approaches the event horizon. The light emitted from such an object will appear increasingly red and faint until it finally disappears. According to the general theory of relativity, a gravitational singularity is located at the center of a black hole, the zone where the curvature of space-time approaches infinity. In a non-rotating black hole, this area takes on a point-like appearance, whereas in a rotating one, it extends in the form of a ring. The density in the singularity zone is also considered infinite. Any objects falling into a black hole will inevitably reach the singularity. Before this, they are subjected to destruction under the influence of increasing tidal forces. This process is called by a funny word, spaghettification, and it immediately becomes clear how an object changes when it falls into a black hole. The gravitational forces acting on the singularity vary in magnitude depending on also on the position of the object. For example, if a person falls into a black hole headfirst, the gravity at their feet will be much stronger than at their head, leading to significant vertical stretching of the body. Despite the obvious merits of the theory of relativity, it encounters difficulties when it comes to events hidden beyond the black hole's horizon. Quantum mechanics, which studies the micro-world of particles and interactions, often contradicts Einstein's theory. Scientists have long sought to unify both concepts within a unified theory of everything. One of the well-known approaches is string theory, but there are alternative options. One such direction is the theory of loop quantum gravity. According to this approach, there is no singularity inside a black hole, giving way to a Planck star. What is that? Instead of completely disappearing, matter continues to compress to a certain limit set by the universe. First, it shrinks to the size of an atom, then to an even smaller volume, greatly exceeding the density of ordinary matter. The compression process reaches the limit that nature itself allows, leading to a state billions of times smaller in size. Atom. In this state, matter will remain for exactly as long as it takes light to cross its diameter. In fact, this is a minuscule amount of time, measured in fractions of a second. Then the reverse expansion will begin. That is, the universe compressed, collapsed, then reassembled and was reborn again. Such is the reincarnation. However, inside a black hole, time flows differently. It almost comes to a standstill. Therefore, a moment inside will correspond to billions of years outside, making the Planck star eternal for external observers. Even to those who are superficially familiar with physics, it may seem paradoxical that light, which has no mass, experiences attraction. However, the general theory of relativity explains this phenomenon differently. The force of gravity is an illusion, a result of the alteration of the unified space-time. Light always moves in a straight line, but the presence of mass causes it to follow curved paths, which remain straight for the light itself. This was experimentally confirmed during a solar eclipse in the early 20th century. Inside a black hole, beneath the event horizon, space-time is so strongly curved that all light paths are directed towards the center. That's why light cannot escape a black hole, regardless of the direction it travels. An interesting fact is that GPS satellites adjust their time readings because mass affects not only space but also the flow of time. The influence of gravity slows it down, and the stronger the gravitational pull, the slower the clocks run. You might not notice this in everyday life, but if you were to embark on a journey at near light speeds, you would return home after a few hours of personal time, while a decade would have passed on Earth. By the way, this concept is depicted in many science fiction movies. Under their own gravitational force, massive stars can collapse. When a star's energy reserves are depleted, and it loses the ability to resist gravitational force, the core collapses, forming a black hole with a monstrous gravitational field. Even larger holes can form as a result of catastrophic collisions of stars. Using a large Android collider as a particle accelerator could provide the opportunity for the creation of microscopic black holes as a result of high-energy particle collisions. Although such experiments have not been conducted, many scientists doubt the likelihood of such a scenario. Astrophysicists studying black holes have recorded powerful emissions coming from supermassive black holes, which they have called jets. Current scientific research is focused on the detection and analysis of gamma radiation, which is presumed to exist in the vicinity of black holes. Astronomers have also recorded cosmic phenomena manifesting as emissions of powerful plasma jets, where particles move at speeds close to the speed of light. These emissions are called jets, as well as giant bubbles of gamma radiation emanating from supermassive black holes. In 2010, researchers from the Harvard-Smithsonian Center for Astrophysics discovered similar bubble-like formations in our galaxy. The sizes of these structures reach up to 50,000 light-years, and their age is estimated to be millions of years. The formation of these cosmic bubbles is likely related to the activity of the supermassive black hole at the center of the Milky Way. Today, astrophysicists observe hundreds of such jets, these rapid streams of particles emanating from the centers of active galaxies, where supermassive black holes are located. These streams are striking in their size. 10 years ago, scientists discovered that the length of one of the jets emanating from the black hole in the galaxy Pictor-A is 3 times the diameter of the Milky Way. Stephen Hawking, the eminent astrophysicist, in the 1970s, posed the question, can black holes emit heat? To estimate the temperature, he used approaches that combine Einstein's theory of relativity, which explains gravity on a macro level, and quantum mechanics, which unveils the mysteries of the micro world. Quantum mechanics suggests the constant emergence and disappearance of particles and their antiparticle counterparts throughout the universe. Usually, such pairs have a very short lifespan, as the particle and antiparticle quickly annihilate each other. However, at the edge of a black hole, the situation changes drastically. The powerful gravitational field affects the vacuum, allowing pairs of particles and antiparticles to survive longer. One of the particles is drawn into the black hole, while the other is propelled into space. The particles leaving the black hole form what is known as Hawking radiation, while the particles absorbed by the hole carry negative energy, effectively taking it away from the hole itself. In other words, Hawking demonstrated that black holes lose mass and energy, which means their gradual disappearance in the distant future. However, scientists have not yet been able to directly observe this radiation. The idea of a massive object whose gravitational pull is so powerful that escaping its influence requires a speed equal to or exceeding the speed of light was first proposed by John Michell back in 1784. In 1784. Year. In the 20th century, Albert Einstein predicted the existence of gravitational waves, which are disturbances in the fabric of spacetime caused by powerful cosmic cataclysms in the early universe. Einstein believed that such oscillations would be barely detectable and almost impossible to discover. However, it turned out that this was not the case. In 2016, scientists managed to detect gravitational waves for the first time, generated by the collision of two black holes, each with a mass 30 times greater than that of the Sun. This event occurred at a distance of 1.3 billion light-years from Earth. 3 years later, in 2019, the first direct image of a black hole in the galaxy Messier 87 appeared, captured using the Event Horizon Telescope. As of today, the nearest known black hole is located approximately 1,500 light-years away from us. The lifespan of each individual black hole is directly related to its mass. The larger the hole, the longer the process of its evaporation lasts. Scientists believe that as a black hole increases in size, it extends its lifespan. Here, an analogy can be drawn with an hourglass, where the upper reservoir symbolizes the remaining time of the hole's existence, gradually absorbing stars and gas. The black hole fills its life hourglass, despite the loss of individual particles. As long as there is available material nearby, the black hole can reset its clock, experts add. However, as the universe ages, the reserves of matter deplete, and the black hole's doomsday clock will begin its countdown. As it evaporates, the black hole slowly contracts, simultaneously accelerating the emission of particles. This process continues until all the remaining energy is released instantaneously. The last fractions of a second. The existence of the black hole will be marked by a bright flash of light and energy, comparable to 1 million thermonuclear explosions in a confined cosmic area, scientists say. Although by human standards this is a colossal power, on an astronomical scale it is a relatively modest figure. For example, one of the most powerful supernovae, Assassin 15LH, turned out to be 22 trillion times more explosive than the final explosion of a black hole. Regardless of the size of the black hole, its finale is equally dramatic. The only difference is how much time will pass until the moment of the final explosion. After consuming its last victim, all that remains is to watch as the relentless grains of time run out until the end comes. In one of his landmark works, Stephen Hawking proposed the idea that black holes gradually disappear over time by evaporating. However, the question of the fate of all the matter absorbed by them remains open, giving rise to the so-called information loss problem in astrophysics. A group of researchers from the University of New Brunswick in Canada proposed a new theory that could resolve not only the singularity problem but also the information loss problem, as well as provide deeper insights into the mechanism of black hole formation. Based on the theory of loop quantum gravity, this concept views space and time as discrete, consisting of small cells or loops that combine in various ways, creating everything that exists in the universe. The authors used a calculation method developed by Sergei Godunov, a renowned expert in the field of hydrodynamic models. During the experiment, they modeled the process of matter compressing into a black hole, using a dust cloud as the basis. According to their findings, matter, upon reaching a high but finite density at the center of the black hole, is repelled back, creating a shock wave. This wave breaks through the event horizon, causing the black hole to evaporate and dissipate. This scenario unites the laws of quantum mechanics with the concepts of space-time curvature from the general theory of relativity, and also aligns with Hawking's theory of black hole evaporation. The research allowed for the calculation of the lifespan of a black hole, showing that it is significantly shorter than previously predicted. This discovery potentially helps explain the information loss problem, implying that matter returns to space. The authors emphasize that modern instruments can detect traces of such shock waves, which will allow for testing the accuracy of the new concept. If their hypothesis is confirmed, shock waves will become universal indicators of black hole death.